put all the FAQs in there, but I also put in an extra credit lesson on logarithms. And that's because when I say logarithms, hopefully immediately you started to think through all of the properties of logarithms. If I said logarithms and you went, huh? Then that lesson is for you, and it is an extra credit lesson. So you watch the lesson, and there are a few problems for you to do at the end, but in order to make sure that you actually listen to the lesson, which is important because I talk about the properties and I go through it, there's also a secret code throughout. I'll tell you to stop and write down a letter, and there will be a sentence at the end that way I will know that you listened to the video.
Oh, well, okay.
How long is the video?
It's not bad. You can just look on the link. It'll have the time.
Is it more than an hour?
No. Okay. It's just basic properties of logarithms video. Okay?
So like 20 minutes?
I can check later. All right, so that link is right on the Schoology page. You go down to the bottom. It's not for watching right now. It is just so that you know it's there. I'll probably give you till like next Monday so that you have the weekend. But if, like I said, a big cloud went over your head when I said logarithms, watch it as soon as possible. Like tonight's assignment shouldn't take you too long, so you might want to watch that logarithm video right away and get it over with. Because what we're going to do is we're going to use logarithms to solve unknown powers. And if you're not up on all the properties of logarithms, it's just going to make it that much more difficult for you. And I do realize some of you probably had different levels of experience with logarithms depending on what Algebra 2 class you're in last year too, so that'll make a difference. So chapter 3, there's a lot there. We've got exponential, logistic, and logarithmic functions. And one of the basic functions that we had talked about was going to be the logistical function, and you haven't had any experience with that up until this year. So we're going to start, in depth on that probably tomorrow, talking about that logistic function. But logarithmic functions, again, that's a big portion of this, and like I said, watch that extra credit video, get a couple extra credit points, and you'll be all caught up. So overview of chapter 3. We move into a really cool group of functions called transcendental functions, which are fabulous. So in this chapter, we move beyond the algebraic functions that we've been studying, polynomials, rational functions, power functions with rational exponents, and we look at 3 families of transcendental functions. Those are functions that go beyond what you learned in algebra last year, those that are a little more involved. So exponential functions, logistic functions, and logarithmic functions are going to do that. And here we have our bullets of individual topics that we'll cover with exponential and logistic functions and their graphs, exponential and logistic modeling, which means word problems, of course, logarithmic functions and their graphs, which you had some experience in Algebra 2 with graphing logarithms, not a ton, so it'll be good to get a little bit of extra help with that again. The properties of logarithmic functions. Like I said, you need to know the basics already. We're going to go above those basics. Equations, solving and modeling using all of these, and then the mathematics of finance, because finance is actually where the natural logarithm, the natural base, and natural logarithms came into being. So we need to know all that good stuff. Pardon me, I used to talk over break here. Exponential and logistic functions. The first section obviously doesn't cover all of that stuff. That was for the whole chapter, but what we want to be able to do is write and use exponential and logistic functions, graph and transform exponential and logistic functions. We're going to kind of chunk that up today, and most of our time will be spent on the exponential part of that. Understand and use the natural base heat, Euler's number. Use exponential and logistic functions to model population growth. So today's focus really is on the exponential functions. So let a and b be real number constants. An exponential function in x is a function that can be written in the form. I'm going to stop there to help you get caught up for a second, because every once in a while somebody confuses power functions with exponential functions. And those are 2 very different things. The difference is the location of the variable. So when we look at this, it says f of x equals a times b to the x. I need everybody to notice the location of the variable. It is now the power. And when we work with unknown powers, That's generally when we have to use logarithms in order to solve. So there's a big difference between a power function and an exponential function. A power function would look like this. F of x equals x to the 7th. That would be a power function. That's not what we're dealing with here. Again, the difference is in the systems that we have to work with as we're going through this. A is non-zero. B is positive. Now that's going to be important for some of the problems that we do today. Our base is going to be positive and not equal to 1. The constant A is the initial value. Makes sense? If we were to put a 0 in here for the x, anything to the 0 power is 1. We get A times 1, which would just give us A right back. And B is the base. So the base, we're going to say, is going to be greater than 1. It's going to be positive, not greater than 1. It's going to be positive, so greater than 0. And B, not equal to 1. If we just multiplied by a 1 as a base, we're not going to change it no matter what we use for a power there. So, first thing we have to do is be able to tell the difference between. Generally, they try to draw you in with the power functions versus an exponential function. So identifying exponential functions, we want to determine whether each of these is an exponential function, and for those that are, that meet the requirements, identify the initial value and the base. All right, so take a look at A, exponential or not. Yep, there's our x for power. So initial value would be 0 something. What's the something? 1. No. There's a little imaginary 1 in front of this whole thing here. And that's our A value, A times B to the x. And then the other thing they wanted to know is, what is the base? So what's the base in this one? Sorry, I was writing, I probably didn't hear you. 3. Yeah, the base is 3. How about B? Is that an exponential function? No, this is not. The variable is actually part of the base. It's not the power. So this is a no. It's not the exponent that we needed to put there. How about C? Exponential function. Yeah. Initial value 0. What? 2. And they also wanted, try to write parentheses here, they want the base. What's the base for that one? 1.5. D. Yes?
Yes.
Is it okay that it has a negative in front of it? That's not okay. But we know how to deal with that. What do negative powers do for us?
Fractions.
They're reciprocals for fractions. Now it looks like that A times B to the x format that we wanted it to have. So initial value 0, what?
7.
Base. So it is exponential. We would want to rewrite it in our form A times B to the x. E. No? Okay. For the purposes of what we're going to do, this is a no. And that's because to our 3 decimal places in pre-calculus, pi would be a constant in 3 decimal places. I'm going to tell you that that changes in calculus. In calculus, pi is not considered a constant because it's still being calculated as I speak right now. They're still calculating pi, you know, there were 10 million, 100 million digits. It's still running. So, for what we have, for the math that we need to do, 3 decimal places, it will be a constant. In theory, pi continues on forever. So just know that when you get to calculus, if Mrs. LaRue is teaching you that pi is not a constant, that's because in calculus you're using more than just those 3,000th digits that we are talking about here. Now, it says one way to evaluate the exponential function when the inputs are rational numbers is just to use the properties of exponents. You know, think about all of those properties of exponents that we had. So if we're computing exponential function values for rational number inputs, this is saying x needs to be a 4. So you can do 2 times 2 times 2 times 2. And just use the property and get your 16 that way. Plug it in. I mean, if you see that it's a 0, 2 to the 0 is going to be what? Yeah, remember by definition, anything to the 0 power has to come out to be 1. Negative 3. You remember what we do with that? Make her a fraction. Get rid of that negative. It's usually easiest to do it. And then go ahead and raise it to the 3rd power. Can we distribute that 3 to both the top and the bottom? Yeah, there's no addition or subtraction here. When it's pure multiplication or division, we're okay. So that'll be 1/8. Scroll up here. F of 1/2. What on earth does that mean? It is square root. It is the square root of 2. So we also write it like this. Just leave it as 2 to the 1/2. In calculus, we're actually going to ask you to leave that with radical right now. But in calculus, sometimes you need to have a power in order to do the calculus. So there will be times when you might want to just use 2 to the 1/2. And what Mrs. LaRue has said before is that you would have to know the difference because this would be on the multiple choice portion of the AP Calc exam. You would have to know that these two are really the same thing because one of those answers will be there and the other one won't. So you just have to know that those two things are equivalent. Alrighty, how about 2 to the negative 3/2? What do you want to do first? Put it on the bottom. Square root next. So which way do you want to go first? You can do it both ways, everybody. It looks like some people are getting confused doing it that way. Do you want to do the cubing first? It doesn't matter. You'll get there. Square root of 1 over the square root of 8. And then, again, this book says math-wise, they would be okay with you stopping right here and saying it's 1 over the square root of 8. I went ahead and simplified the denominator. In Algebra 2, you know that we would just go ahead now and multiply the top and the bottom by the square root of 2 because we don't want to leave that there. Again, on the AP exam, Mrs. LaRue says you have to know that they would all be the exact same thing. You have to be able to go through all of those steps and know that they would be the same thing on a multiple choice test. That kind of bugs me to leave this. So we would have 1 over 2 square roots of 2, and we'd multiply by the square root of 2 on the top and the bottom, so it'd be the square root of 2 over 4 in simplified form. So on those AP exams, you could see this, you could see this, you could see this. You have to know that they're all equivalent. All right, what if it's pi? That's an exact answer. Most of the time we're going to turn it into a decimal because we want this to thousandths. I mean, that's what we're supposed to be doing is the 3 decimal places. So 2 to the pi. 8.825. Round into 3 decimal places. Square root of 3. Can you raise the number to the square root of 3 power? Same type of thing. I'm going to plug it in the calculator and let the calculator deal with it. So 2 to the square root of 3. 3.322. So we can do it. It's not beautiful or anything, but we can figure out what it is to our thousandths position. So now we're talking about exponential functions. How are we going to know when we're dealing with an exponential function? Well, most of the time we're going to look at it and we're going to say, you know, this is a curve that's happening here. This is not a line. So we would try to use models that deal with things that are curved. It's not a parabola, pretty obviously. So next thing we'd say is, hey, this looks like exponential growth and exponential decay, and that's what an exponential function does. So it says determine formulas for the exponential functions g and h plus u, whose values are given in table 3.2. How do we find the initial value and the base? Because that's what we have to do. Our formula, remember, is f of x equals a times b to the x. So when I'm trying to write a formula for, in this case, just g of x, I'm looking for the initial value. Well, the initial value is always what you get when you put 0 in. What did you get when you put 0 in? A 4. And then everything gets multiplied by that same base every time. And they already did the math for us here to show us that each and every time what's happening here is they're multiplying by a 3. And I tend not to use dots. This book, I think, still uses dots occasionally for the multiplication, but I don't want anybody to think that that's a decimal. So this one is called h of x. So what would we start with for h of x? 8. 0, 8. And then what would our base be? 1/4. That's what they're multiplying by every time. And then we just want to slap a little x up there. So it's not incredibly difficult, you know, especially if you have a table that's used 0 to figure out what that exponential function could be modeled as. But pretty obviously, they're not going to come to us all nice and prepackaged and, oh, look, they multiplied everything by 3. Oh, look, but it wouldn't be that hard to get because all we would have to do is make sure these are going by the same interval every time and just divide to get that if we had tables. Now, what if they don't even give us that? What if they say, here's a couple of points, write an exponential function for this little bugger. Find the exponential function f of x equals a times b to the x, whose graph goes through the points negative 2, 10, and 2, 1/3. Here's the first thing I would look for. Even though they wrote it this way, did they give me the initial value just by mistake? You know, and how I'm going to look for that is I'm going to look for 0a. Bad news. All right, so what can I do? Well, I have this model to start with, and I know this is uppercase instead of lowercase, but just so that it was better readable as you want to do that. So I look at this and I think, well, if I put these in for x and y, it would look like this. Ten equals a times b to the negative 2. And if I put in 2 and 1/3 into the other one, it'll be 1/3 equals a times b squared. I have 2 equations and I have 2 unknowns. So I need to use these together to find out my a and b. And I realize, well, substitution would do a pretty good job with this. I mean, if I could figure out how to make all this work and use substitution, then I can do that. So, I guess I'd really like to replace that in that second equation. To start, I'm going to rewrite this, because b to the negative 2 should go down to the bottom. Remember that negative power is for reciprocals. Well, this is going to be super easy to get a all by itself. All I have to do is multiply both sides by b squared, and I'll have a all by itself. that in the other one. So I have 1/3 equals 10b squared b squared. I don't know about you, but I want to simplify those two b squareds right away. All right, so to keep going, I would have to divide both sides by 10, but we have a fraction on it. So you don't divide, you multiply by the reciprocal. This will be gone. Ew, this is not going to be pretty. Because what do I have to do to get b by itself? Fourth root of 1/30 is going to be b. Well, the fourth root of 1 is just 1. That's not a big deal, but I've got the fourth root of 30 down there on the bottom. But that's good news. We know what b is. B wasn't the only thing we needed, right? What else did we need? So we need a formula up here that was really nice, easy looking to find a. And that's this formula right here. So this will be 10 times 1 over the fourth root of 30 squared. It's going to give us a. All right, so 10. 1 squared is just 1. Good gravy. Fourth root of 30 squared. Well, this is where you want to think of this in terms of fraction powers. Right here? Yep. But to solve for a, to get a by itself, we multiplied both sides by that b squared because we wrote this as a fraction. You can do it the other way too. It's just a matter of which formula you want to go back to. When you're working with radicals and you're raising them to other powers, you have to go with fraction powers. It's just the easiest thing to do. So we're going to change this fourth root of 30 to 30 to the 1/4. And then square it. Because when you square, we have pure division taking place in here, and we can distribute that power. So this will be 10 times 1 over 1/4 times 2 is 2/4. That's going to be 30 to the 1/2. And now, because we had left b in terms of a radical, we should change this to a radical as well. You don't want to mix and match. If you're going to do fraction powers all the way, do fraction powers all the way. If you're going to do radicals all the way. So we'll have a 10 on the top and the square root of 30 on the bottom. It's not pretty, but we now know what a and b are supposed to be. So, did they give us a name for this function, or could we call it whatever we want? F of x. We'll stick with the f of x. Equals our wonderful 10 over the square root of 30 times 1 over the fourth root of 30 power. Yeah, it's ugly, but it's ours.
So how did you distribute that?
Oh, we can't, because this is now a power, because it has an x as a power, and this is just a number. 4. Oh, top times top, bottom times bottom x. Do I just slap a 1 underneath that? Then I can get that. Now, here's the thing again. This is the root it said. Yes, you could see it like this, but remember, you could see it with the fraction powers as well. And you have to know that they would give you the same thing. So you want to be able to write it either way as you go through there. Now, what else could you see? Well, take a look at that. Where did I get that from? Just putting this into a different form. So 10 times 30 to the negative 1/2. times, this would be 30 to the negative 1/4. I can just use one set of parentheses there. So now what could you see? Well, we have the 10, but we see we have a base of 30. And if both of these have a base of 30, what we can do is we could put those together as one base now. So our 30 to the negative 1/2 would just stay here for a second. But this could become 30 to the negative 1/4 x. And that's because when you raise a power to a power, you always multiply. This is something, like I said, I talked through in the extra credit video as well. And since those 30s both have the same base, we could see this written as 30 to the negative 1/4 x minus 1/2 power. So lots of varied ways that they could write the answer to this. And you just have to look at it differently and say, hey, how could I simplify all of this? That we can't, because one is an x and one is not. So we can't put those two pieces together. So we had this as a correct answer. This as a correct answer. And this as what would probably be considered as a simplified answer, because we have 30 there as one base. But all three of those would give us the exact same exponential function. Like I said, we talked in depth with Mrs. LaRue about this, because we said, is it good enough to stop you guys right here and say, hey, it's done? And she said, well, they need to know that if they don't see this for an answer, that it could be this one or it could be this one. So it's just a little algebra manipulation to keep you going. All right. And I think the answer to, I'm going to give you one of these today in the homework. I wrote it all three ways, so that whatever way you want to check it, yeah. So values for a general exponential function. What we're looking for is, where's that a value, 0a, and then we're trying to figure out what did they multiply by each time. And that pattern leads to, like it says, a recursive formula for exponential functions. It shows you how to get to the next number without necessarily getting a formula. All we're doing is we're multiplying by b each and every time. So for any exponential function, f of x equals a times b to the x and any real number x. Let's say we don't want the 0, we want the first power. Well, if this is a 1, then you're going to end up with b to the first times the last number that you just had. Recursive, if you remember from sequences and series last year, means using what you already have to get the next number. And that's what's going on here. They're saying, you know what, if you want the next one, just multiply by whatever b was, and you'll have it. If a is greater than 0 and b is greater than 1, f is increasing, and we refer to it as exponential growth. So it starts small and starts going up really quickly. So exponential growth function. The base b is its growth factor. How much is this going up by each and every time? If a is greater than 0, so still a positive 0a value there, but b is less than 1, well, now it's dropping, it's decreasing, and that's called an exponential decay function, and the base b is now called its decay factor. So exponential growth explains things like bacteria. Exponential decay is going to explain things like carbon dating. We're trying to figure out how old something is. That's going to be with carbon dating. And our exploration down here is something that you actually had to do back in Algebra 2. You had to graph them, and then we talked about their overall look. But what you didn't do in Algebra 2 was our analyze. So we want to analyze the functions for domain, range, continuity, increasing or decreasing, behavior, symmetry, boundedness, extrema, asymptotes, and end behavior. So if you have your graphing calculator with, we're going to punch in these 4 functions. And for some reason, they're giving us a viewing window from -2 to 2 and -1 to 6. I don't think it matters if we use zoom 6 for any of these. So in our y equals 2 to the x, 3 to the x, 4 to the x, and 5 to the x. So as I look at this, I'm realizing, well, what are they trying to get me to see? What they're trying to get me to see is what happens when b is positive. 2, 3, 4, and 5, all nice and positive. Zoom 6 to the x, 3 to the x, 4 to the x, and 5 to the x. And we can see the overall behavior, just because they're positive, is the same. So we're supposed to analyze this for domain. Do you think of any numbers that we could not use in the real number system for the power on those? No, we can use negatives. We've been doing that. That's going to be for reciprocals. So negative infinity to infinity. We using all the y's? No, we're not using anything below the x-axis. So how should we put that? Now, do we want brackets or parentheses on the 0? Why parentheses? Good. Some people are thinking backwards. They're going, okay, 1/2, 1/4, 1/8. Wait a minute, I'm never going to get actually to 0. Yeah, so we'll never actually get there. 0 to infinity. And continuity. What do you think? Continuous or not? Yep. Remember, that just means we can draw this with a pencil without having to lift up our pencil at one time. Increasing, decreasing, both. What do you say? Increasing. Always? Yeah. Negative infinity to infinity. All right, how about symmetry? No, we don't have our even, which is reflecting over the y-axis, or our odd, which is reflecting through the origin, so no symmetry. Boundedness? It is bounded below. What would it be bounded by? Y equals 0, the x-axis. Bounded below by y equals 0. Extrema. Local max is local max. Okay. How about asymptotes? Just talked about one, right? Yeah. Horizontal asymptote. Y equals 0. Any others? Okay, and then end behavior. I didn't leave my stuff enough room here. Switch that down. Oh, I don't want to scroll up. Was it f of x? So in general, we'll just call it f of x because we want to have a function to talk about. All right, so as we go to the left forever, where is this going? As we go to the right forever. And that was true for every positive base that we just went through. All of that analyzed was the same for any of those. The 2, the 3, the 4, and the 5, all the same. So, take a look at these. Do we have to pop them into the graphic calculator, or do you know what you're going to see? Let's make a little sketch. What's it going to look like, everybody, if our bases are 1/2, 1/3, 1/4, 1/5? This is decay. You're going to start high. And it's going to go down low. Okay. Ever going to pass that 0 mark? No. And it makes sense if you think in terms of word problems, because in a word problem, this would be the carbon dating, the carbon is getting smaller and smaller and smaller. Is it ever going to approach zero? Well, scientifically they'll say it'll get really, really, really close, but it's never going to get there. So our analyze, which point would be common to all four of these graphs? Take a look at the ones we just did before. What did they all have in common? 0, 1. Same thing for this one. That's their all the initial value. We don't see an initial value up there for any of them, so it would always be 1. Domain, what do we put? No bad X's. Range. Zeros are cut off again. Yeah, do we include 0? No. Again, it's that theoretically it would never quite reach 0 piece there. Continuity, is it continuous or not? Yes? Continuous? Increasing or decreasing, or a little bit of both? Decreasing. Over the entire domain? All right, symmetry. Nope. No symmetry. How about boundedness? Bounded below again? Bounded below by what? Y equals 0. Extrema. Local max, local min? Okay. Asymptotes, just said one. Any more? Just a horizontal asymptote? All right. And end behavior. As you go to the left forever. Infinity is going up as we go to the left. How about as we go to the right forever? That's our 0. Closer and closer to 0 over there. So, it would seem, if we just take a look at the base, we should be able to analyze these the same way. It's like all the positive bases do one thing, and all of the fraction between 0 and 1 bases do another. But they have that same basic shape. And that's what we see in this lovely yellow box on the next page. Which is the domain all reals. The range, 0 to infinity. They're continuous. Neither even or odd symmetry. Bounded below but not above. And no local extrema. Horizontal asymptote of y equals 0. No vertical asymptotes. No breaks in that domain. If b is greater than 1, then we have the increasing and we see our limits there. But if b is a fraction between 0 and 1, that gives us decay. And that's why our limit behavior changes on that.
What would be an example where there is a vertical asymptote?
It would have to be a piecewise function. We would not be seeing just one exponential function that would have a great limit. Let me give you an example in the world. Somebody's strep test comes back negative, and the bacteria are growing too slowly, but the person comes back in the next day, and for whatever reason, they can't get enough on a swab. What they could do is take a petri dish and take 2 samples of the day old and see if that affects the growth and see if it changes at all. So it's kind of the reason they do the overnight thing as well when you get the first strep test. It's because it just might be that it needs a little more time to start multiplying. Along those lines. Using transformations from chapter 1, translations, reflections, stretches, and compressions. We have described how to transform our basic graph of f of x equals 2 to the x into the graphs that we see here, and sketch the graphs by hand and support our answer with the grapher. So, if for g of x we have 2 to the x minus 1 and f of x equals 2 to the x, where does that graph go? How does it change? 1 to the right. our normal 2 to the x, our parent function, we know is going to go through 0, 1, then it would go through 1, 2, and 2, 4. And all we would have to do with those points is just move them 1 unit to the right to make it solid. So using what we know about translations, transformations in general. B looks a little weird. What happened to that graph? Put that negative up there. Yeah, flipped over the y-axis. Remember, it's always the opposite of what we see. So if this negative is in front of the x, this actually reflected over the y-axis. So let's put our nice little 0, 1, 1, 2, 2, 4 up there. And go equal but opposite on the other side of the y-axis. Just like so. Was that supposed to be decay? I mean, at this point, you should ask yourself, is this really representing decay up here? Yeah, the negative would change that to 1/2 to the x column. So that would be decay. What changed transformation-wise when they put that 3 in front of it? What did that do? That is a vertical stretch, factor of 3. So we start off with our normal. Vertical stretch. So what it's going to do is it's going to take our y values and it's going to multiply that y value by 3. So this isn't going to be 0, 1 anymore. It's going to be 0, 3. And instead of 1, 1, it'll be 1, 3. Hang on. What did I have before? 1, 2. I thought that was 1, 1 that I had there. It's 1, 2. 2, 4. There we go. 2, 3, 4, 5, 6. That's probably enough. Get a good look at that curve. So basic transformations are not changing. They're not. What we care about is it growth or decay? And it said, what if the base of 2 in the last problem was replaced by 2.71828? Would they change much? Left this one up here. Take a look at that. That was 2 to the x, 3 to the x, 4 to the x, etc. Still going to be growth, right? I mean, it's just closer to 3 if we were to round that. So would they change much? No. But we are supposed to recognize 2.71828. It is Euler's number. It's E. It's the natural base. So what we're saying is, just because we go from an integer base to natural base E, it doesn't mean that that's going to change everything, because it's not. It's just a matter of what is that base. Okay, rats. So I had hoped that we would get to example 5. Not get there. But this will go pretty quick tomorrow. So unfortunately, that means you're probably not going to be able to do all of the assignment. I know that's a killer.
Oh, darn.
But do what you can, and then maybe watch that extra credit.
47 minutes of it.
It's not 47, is it? Oh, you know why? Because at the end, I just let it sit there so you could write down the problems. Let it sit there for a while. did this assignment over break, though you might be able to do all of this.